Okay, well, if we draw, we know it's first order, we've got a concentration versus time table. If it's first order, then we know that the log of the concentration is equal to minus kT plus the log of the initial concentration. So, in order to plot that as a straight line, what we're going to do is we're going to plot the log of the concentration on the y-axis, and we're going to plot time on the x-axis, and then it'll give us a slope which is minus the rate constant. So, write up another table where you do the log of the concentration against time. Then you're going to plot your graph. Your slope is going to be negative again. It's going to go down. So this is time on the x-axis and the log of your concentration. See, sorry, I've been using A and C interchangeably. What I really mean is concentration. And we can do that directly from this. We've got concentration, time, so we can plot that graph, and the slope is minus the rate constant. But I actually did this a different way because I didn't read the question properly, and I noticed that we've got here, it tells us it's first order, and here we've got the reaction decreasing to half its initial concentration. So if you see that, you immediately think of half-lives. And that means the time it takes for the concentration to decrease to half its initial concentration is the half-life of reaction. And that means its half-life is 72 seconds. So we can say for this reaction, we know T a half is equal to 70 seconds. But you also know, because I'm sure Mike's given you this equation, that the half-life for a first order reaction is given by log of 2 divided by the rate constant. So that's equal to 70, which means our rate constant K is given by the log of 2 over 70, and that comes out to be 0.0099 seconds to the minus 1. That's what I get with a half-life, and that's what your slope, your graph should come out to be. Okay, what we're actually after is the pre-exponential factor. So, how do we get the pre-exponential factor? Well, we've got all the information we need now. It's really just a matter of substituting it into the equation. So what we know is that for our reaction, our rate constant is going to be given by A exponential the activation energy minus over RT, and we have all this information. Our rate constant we just discovered is 9.9 times 10 to the minus 3. That's going to be A times E. Our activation energy is 50 kilojoules per mole. Don't forget it's kilojoules per mole, but you always, in a calculation, you have to, it's joules. And the reason for that is that R is in joules, so it's 50,000 on the top there. R is 8.314, and temperature, you can tell us 296. I don't know if I did this calculation, I didn't. Plug that into your calculator and you should get an answer, but I haven't got it for you. Okay, any questions on that one? Fine. I think I've just got one paper left now. Right, this will help you because there's a lot of questions here. And this is CH2 101. Before we rearranged the first year, the Kinetics and Spectroscopy lectures were in a module called 2101. And that was in the can't remember which semester. I think it was in the autumn semester. Only a couple of years ago, and I can't remember already. Anyway, so if you want other examples of kinetics and spectroscopy questions, then look at this module, the previous examples, and you'll find lots of examples. So this one is the recip. This happens to be a recip from from last year, and well, this year actually, and that's because we had a student who was out for a year and came back, and we had to set an exam for them, a special exam for them. So we've got this information. Okay, so we have a particular reaction. Rate constant increases by a factor of 2. When we increase the temperature, well, this is a little bit easier. I like this one. This is exactly the sort of calculation that you had to do in your practical. And in your practical, I gave you a different version of the Arrhenius equation to remember. So if you remember, we had the log K1 over K2 given by minus the activation energy over R into 1 over T1 minus 1 over T2. And again, you can derive that, or you can remember it, whichever suits you best. And now it's just a matter of putting the numbers in. We got K2 is equal to twice K1. T1, the initial temperature is 100 degrees C, which is 273. T2 is that plus 50, which is 323. Oh, yeah.
Isn't it supposed to be 1 over T2 minus 1 over T1?
No. Should we derive it just to make sure? Okay. Okay, so it's going to be K1 over K2 is equal to E to the minus E, EA over R, T1 all divided by, oh, let's just put it up here, times E to the plus EA over TR T2, which of course is going to be, am I right so far? Yeah, good. Which is going to be E, we're going to add these together, of course. What? No. Yes, of course I am. We're going to have EA over R minus EA over R into 1 over T1 minus 1 over T2. Yes, of course I'm right. Yeah. That's fine. Oh, it's good. I enjoy doing that. Is everybody happy that it's this way around now? Of course you are. Good. Right. So having got that, we can now substitute in the numbers. And it's just a matter of, we have the log R is equal to minus, we're trying to find activation energy, over 8.314 into 1 over 273, is it? No, that can't be right. 100 degrees. There we are, that was a deliberate mistake. 423, yeah? And rearrange that, and you find that the activation energy is equal to another 18.185 kilojoules per mole.